Good morning, everybody. So for this last lecture, I will probably intend to go a little bit more into recent works on the structure of data and its importance. I mean, it's a topic that I have been very much concerned with in the last 3 years, or at least. And I would like to start by introducing. Well, we have been dealing actually with ensembles, but maybe not stressing it as much. So I would like to start with a short introductory chapter in which I give you 3 examples of ensembles, 3 examples that we have actually already seen, but in which I will more stress the importance of the ensemble and the choice of the ensemble and what it means. So let me start with codes. I told you yesterday about Shannon theorem, Shannon who had invented the best possible error correcting codes, the one which have the best possible performance, that is they are able to correct errors up to a level of noise which is optimal. You cannot go beyond with any other code. And I didn't explain you what are the codes that Shannon had invented. So I will do that very briefly by this small cartoon. And also it will give me also the occasion to explain better the limitation of Shannon's code. So you remember the setup that we had yesterday about coding. We have a certain code word, we send it through a noisy channel, and then we want to decode it after receiving a certain message. And the idea was to agree between the sender and the receiver, agree on what is called a code book. A code book is an ensemble of code words, and these code words, they have to be decided. So yesterday I was telling you, for instance, about LDPC codes, and the code book was the set of solutions of a certain system of linear equations. That was a simple way of defining a code book. The idea of a code book is that the code words should be far away from each other, so that if you send this code word, it will be maybe perturbed by the channel, so you will send a message which is a bit aside from this guy, and then you will try to find the nearest code word, and that will be your best guess for the message that has been sent. So if this guy is well isolated in space, then you get a good error correction. Now you could think, if you have that image in mind, you could think that, okay, let me sit down for a while in front of the unit hypercube in 10,000 dimension and invent a set of code words. I will have a certain rate, so I am in a space with 2 to the n vertices. I will want to decide that 2 to the r times n, r is the rate, are code words, and the r is adapted to the level of noise that, I mean, if one has a lot of noise in the channel, then one uses code words which are very far away, so r is small. And you should think maybe I will sit in front of that and invent the geometry of the code book myself. That's not what Shannon did, and that's not what is optimal. The optimal thing is just to decide random code words. So basically, in Shannon ensemble, you have n bits. So it means that you have 2 to the n vertices. And you decide that the code book, that is the ensemble of all code words, is an ensemble of 2 to the n times r vertices, selected vertices. Where r is some number less than 1. It is a rate. So you color a certain number of the vertices. These are the vertices that I have put here. Okay. This is an ensemble. This I have not defined a code book. I have defined to you a probabilistic rule that generates a code book. So you take this probabilistic rule. For each of the 2 to the n vertices, you decide to accept it or not with probability 2 to the r minus 1 n. And then you have your code book. You agree on the code book between the sender and the receiver. Now, of course, so this is, the notion of ensemble is crucial. That is, you could have another code book also generated by the same process. Now it turns out that there is a geometrical property that when n is large, in this large dimensional space with this process here, you will generate a very good code. You will generate a code which has geometric properties such that generically the code words are far away from each other. You will generate such a good code that you cannot do better with any human invention. That's nice. So that's a perfect example of the coding, and again, I remind you of the result, so that so if you have the code book, you send this code word, you receive this one, you decode by looking on a sphere of radius Pn. That's all what we did yesterday, and you find that this decoding. So you look on this sphere and you find if there is a code book or code word or not. If there is a code word, you say this is this guy that was sent. And the probability of decoding perfectly in the large n limit, in the thermodynamic limit, you decode perfectly with probability 1 up to a threshold in noise. This is the noise. If you increase the noise beyond this level, it does not work, but below that, it's perfect. And here it doesn't work just because of geometrical properties. The density of code words is such that you have too many. Is it clear? Okay, yes, please. Sorry? There is a theorem that tells you that this is the best that you can ever do. So, and in some sense, okay, now let me make a short comment. I don't want to lecture too much on codes, but it's a wonderful topic. But let me comment on the drawback of this code, because of course it's perfect, but it is extremely, the drawback of this code is that it has no structure. So when you are here, you have no other choice than looking at everybody on this sphere, because you have no hint of where another code word could be on the sphere. So this sphere has exponentially large number of vertices. So the decoding is exponentially slow. So this is the drawback. And basically, all the things that we were doing yesterday about algebraic equations and so on, they were dealing with doing a structure. So it's a kind of lattice, in some sense, this algebraic structure. And the structure should be such that you keep a good distance property between the words. They are far away. But at the same time, you have some algebra, you have some structure that helps you to decode. And that was the belief propagation. So that was to introduce the notion of an ensemble. Let me remind you of what we heard yesterday. I talked about it, and you talked about it also in compressed sensing. So I just remind what we were seeing yesterday. You have an unknown vector of n component x. You do m linear measurements. You have a number of measurements which is smaller than n, but you know one, and you want to reconstruct, knowing y and knowing the measurement matrix f, you want to reconstruct x. You are in the underdetermined regime, but you add something else. You add the fact that x is sparse. So it has a number of non-zero components, which is rho times n. So among the various methods that have been invented to deal with that, and that was described at length yesterday, there is the L1 norm minimization, in which you want to find an n component vector x such that the m equations are satisfied, and the L1 norm of x is minimal. The sum of absolute value of xi is minimal. And there is a BP approach, which is a Bayesian approach. You compute the maximal, you want to find the x that maximizes the posterior probability P of x given y, and you study that by BP. That is what I was describing yesterday. So all this is a kind of general idea. Now you can decide of an ensemble. And the ensemble that I described yesterday, and I was not insisting enough on it, was an ensemble in which the elements of F are IID, Gaussian distributed. If you take this ensemble, then you are able to do statistical physics. You have, in some sense, statistical physics, it is of a disordered system, it is something which is complicated. You have interacting variables, and these variables, they depend on quench parameters. In my case here, the quench parameters will be the value of f. But in order to do statistical physics, I need to describe how I generate the f. And for this, I need a probabilistic process that gives you the f. The simplest one, the one that has been studied, is when f are IID. They could be normal or they could be IID. That was the question of yesterday. They can be IID. Well, if the variance is finite, then it works the same. So under these circumstances, and for this ensemble, you get the phase diagram that tells you that this is the number of measurement and this is the density of non-zero component. There is a sharp phase transition for the BP decoding here. And this phase transition, it is for this ensemble here. So I will come back to the L1 transition later. You have actually much more precise results using statistical physics on this system. You can predict using the replica method. You can compute what is the probability that the reconstructed X is at a certain distance d from the target, from the signal that you are seeking. And with the cavity method, you call it how is it called? State evolution. You show that the order parameters of the BP iteration, they flow according to the gradient of the free energy. So you get an analytic control of the BP equations. And this works perfectly. Here is the error of reconstruction for various value of alpha. So alpha is the number of measurement. This alpha equal 0.56 is not enough, you see, so you get an error which saturates at 0.1. Alpha equal 0.62 is enough, you have enough measurement, and you can reconstruct perfectly the signal. And this is the error that you do as a function of the iterations of the BP algorithm. And these are experimental points and theoretical points computed using the BP method. So all this works perfectly. It works perfectly in an ensemble. Sorry, one thing that I should stress here is that in the L1 norm, you can get this phase transition. So it's a bit worse. You see the L1 will not perform as well as the BP. You can decode perfectly in the BP in this zone here, where you have a number of measurements in which L1 has already entered a regime in which it does not work. But the result for the L1 is much more robust. It does not rely on the ensemble. It relies on some properties of the matrix F, like the restricted isoperimeter quantity, something which has to do with the fact that the columns of the matrix are more or less orthogonal, let's say, or are far away, let's say. So this is more robust. This is better, but dedicated to an ensemble. Last example that I want to show is perceptron learning in the 90s. You take a perceptron. So a perceptron, it has an input layer with n units and one single output. Yes?
The property you were mentioning for L1 method to work, are they satisfied by the ensemble?
Yes. The ensemble is a sub-ensemble of the...
So the ensemble avoids the worst cases of
the RIP. No, it is not that. Yeah, I know. No, I think it is not only that. It is the fact that intrinsically the L1 minimization is not the good thing to do. It is the thing that you are able to do because it is convex. But in principle, that's not what you should do. You should minimize the L0 norm. That is basically, in all what you do, you should look at the subspace, all the X that satisfy Y equal Fx. You have a linear subspace here. And in this subspace, you know that X is sparse. So the thing that you want to minimize, you would say, in this subspace, you want to minimize some norm of X. But the thing that you should do is minimize the norm of X0, the number of non-zero elements. And this you cannot do because it's highly non-convex. So instead of that, you relax it to norm X1. But here you lose. Instead, in our BP approach, we don't use that. We go to something which is different, which is the Bayesian probability approach. And here we don't lose. So the perceptron is here. You have the output is just the sign of a certain, you have a vector J with n components. This is the vector of the weights which are here. You do J times X, and the nonlinear function is just the sign. This is a perceptron. And one system which was, let me tell you of one ensemble that was studied quite a lot and quite useful. It is the following. Imagine that you want to define a task. And imagine that the task that you want to define is another perceptron. And so there is a teacher perceptron. And the teacher perceptron, it is defined by whenever you present X, it outputs sine of J times X. So J is a vector of the teacher. Now, the student, you want to learn, the student does not know the parameters J of the teacher. And during learning, it will, at some point, it will have its own parameter K. And it will output sine of K times X. And here, just to make things simple, to give a simple example, I go to the case in which J and K are binary vectors, binary entry vectors. So you study that with machine learning. That is, you present a database of examples, X mu. There are P examples. I present it at the input. For each example, the teacher knows the output. It's Y mu. And so the students knows what? The students knows what is the value of X mu, what is the value of the output. Knows the input-output, it's supervised learning. And the student with that starts to learn the components of K. So it's binary, so you cannot do stochastic gradient descent or whatever. You have to do some tricks, but okay, do it as good as you can. And then you compute the generalization error. Of course, the generalization error, it will be 0 if J equal K, and it will basically depend on the angle between J and K. That is obvious. Now, in order to do this computation completely, I need an ensemble. I need to decide what is the data that I am providing to this system. And the data that has been studied, again, I go back in 1990 here, following works by Derrida and Gardner and so on, and Georgi, who has done this computation here. He picked up an ensemble in which you take IID xi mu. Could be normal, could be binary, doesn't matter much, but they are IID. It's for each mu and I generate independently of all the others the component. When you do that, Georgi showed in 1990 using the replica method that the generalization error as function of alpha, so alpha is the number of examples that you have been providing, the size of the database, divided by the number of input neurons. Okay? So when alpha increases, you have more and more data, and the student finds a K which approaches J. So you find that the generalization error decreases, and then there are really two curves here. The optimal generalization error, that is the best that you can do with the data that you have available, it is the red curve, and it will have a certain transition near to alpha equal 1.25. So if you have an amount of data which is larger than 1.25 n, and you have perfect learning, you are able to basically to explore the whole landscape of the K, then here you generalize perfectly. You have understood the task. So this is nice, it's a sharp phase transition. Now there is another curve which is the green curve, and the green curve is actually what happens when you learn the K using belief propagation, or AMP. And you see that you find exactly the optimal result. Then above 1.25, it does not realize that it has enough data. It has to go beyond, and it has another threshold at 1.49, where it has a transition to perfect generalization. So here there is, you see there is, again, there is these three phases that I was showing you recurrently yesterday. There is an easy phase. If I have an amount of data which is larger than 1.5, then the system is easy, and even my simple-minded belief propagation, AMP thing, converges fast. There is a hard phase in which there is no way I can generalize because I don't have enough data. And there is this intermediate phase in which the optimal algorithm should be able to find it, but the algorithm that I have at hand, the one that I can really run in polynomial time and so on, is this one, and it is not yet able to find it. Easy, hard, impossible. So the points are the numerical experiments, and I should state that this was shown with replicas in 1990, and last year Barbier and his collaborators were able to prove all that completely rigorously using methods that I will not try to describe.
When you say it's fast, it's like the number of iterations when you are in the easy phase.
Linear. It's very fast. Okay, so just to summarize this kind of introduction about ensembles, I wanted to stress this, that if one thinks in some sense of what statistical physics can bring to these fields of machine learning, constraint satisfaction problems, and so on, they are really the strong statements that we can make are statements about ensembles of problems. So we have to, and then when we have a good ensemble of problem, then we can make, invent new algorithms, control them, have all the control of the thermodynamic limit, the phase diagram, and so on. So this complements, in some sense, the other approaches that you can have. It is nice, but it relies a lot on what are the ensembles that can be studied. What are the ensembles that have been studied, and does it matter? And I will try to address these various points here. So I will start with a simple example, which is going back to the Hopfield model of neural networks, a Hopfield model with structured patterns. And then in the next chapter, I will go to machine learning, much more elaborate things. So for those of you who are too young to have heard about Hopfield model, in 1980 something, 83 maybe, John Hopfield, 84, John Hopfield came up with a simple model of interacting spins that he thought was a good model for describing what happens in the brain in terms of associative memory. And his model, I will make it very short, he models the neurons as binary spins. The neuron can be active or inactive. So active means that there is a spike, there is a depolarization wave along the axon of the neuron, or it can be non-active, so it's plus or minus 1. And imagine that you want to memorize, so you have a network of these neurons. These neurons, they interact by pairs, so yeah, they have an interaction energy, like an exchange coupling between spins, Jij, SISJ. And you will look at them at a thermal equilibrium, so the probability of a certain configuration of the neuron is this one. So just a system of Ising spins interacting with coupling Jij. Now what he wanted to do is memorize in this model, memorize a set of patterns. So you have the pattern psi I mu, I goes from 1 to n, mu goes from 1 to p. And his proposal was to introduce a structured matrix of couplings. So far, if you look at the left-hand side, this is just a spin-glass model. And actually, if you decide that you study this problem with Jij, which are IID normal, this is the celebrated Sherrington-Kirkpatrick model, on which there has been so many nice pieces of work, very much studied and so on. Now he does something slightly different. Instead of saying that Jij is IID Gaussian, he picks up Jij, which is of this type. It is a superposition of the patterns. So you look at the sum of all the patterns, the activity of pattern mu on neuron I, activity of pattern mu on neuron J. And then he's able, doing that, to show that there is a phase in which there is a regime of, so there are two parameters, the parameter beta, which is the inverse temperature, and the parameter P over N, which is the number of patterns that you want to memorize. So there is a phase diagram. And in this phase diagram, there is a nice phase in which there are the low-lying states are the patterns, and they are attractors of the dynamics. So basically, this works as an associative memory. You will start maybe from a certain configuration S, which is not too far from a pattern, and it will flow nicely under Langevin dynamics or whatever dynamics you want, Monte Carlo dynamics. It will flow towards a pattern. So this is nice. It was a kind of new concept of associative memory. I want to tell you something about, so it means that this model has a phenomenology which is different from the SK model. In the SK model, you don't have this convergence on well-defined patterns. So it means that the structure of the disorder, of the quench disorder, the JIJ, it matters a lot. I have a new ensemble here. It is like actually it's like a Wishart ensemble, and it is different from the simple Gaussian ensemble. It's completely different phenomenology. I will look at it by looking at the mean field equation that I was describing yesterday, and these are the TAP equations. And so the TAP equations, they are self-consistent equations relating the local fields. So you have the local field on spin I, and the magnetization on spin I will be tanh beta HI. HI is a local field. And the TAP equation, they are just saying the local field on HI, it is the sum over all the other spins of the coupling constant JKI times the magnetization on the other guy. That would be the very naive equation. If you would sit down and write a naive equation, you would say the local field here, it is the sum of the influence of all the other spins. And I average it, and I say that it is just the sum of JKA MK, the magnetization. So that would be a naive equation. It turns out that there is a reaction term, and the reaction term due to Onsager and discovered really by Thouless, Anderson, and Palmer, has this form here. Does it work when you take the J, which have the structure of the Hopfield model? The answer is no. These equations, they are okay if you look at the SK model, if the J are IID Gaussian. If the J are not IID Gaussian, they are just wrong mean field equation. And the reason is the following. In the TAP equation, what you take into account is this term here. This term is just to compensate for the fact that I can polarize J, and which retropolarizes onto I. You have to subtract that. That is what is being done here. This is basically the reaction term. Now, this is the only reaction term that you have to take into account if you have the Hopfield model. If you have the SK model, if you have the Hopfield model, you have more complicated reaction term, because basically you can have I polarizes J, which polarizes K, which polarizes I. And this is true. This you have to take into account, because with this matrix here, you have non-zero triplet correlation. You have a triangle which is non-zero, and so it creates a lot of circuits of interactions. So one way to write the TAP equations is to do something that was mentioned yesterday by Simona, is to describe the Hopfield model in terms of auxiliary variables. So it's just a couple of lines of algebra. I will not go into the detail. But basically, if you look at the partition function of the Hopfield model and you inject into that the structure of the coupling, you can write it like that, a sum of all the spin configuration. And then the Boltzmann, the energy is really the sum of the patterns mu, sum over I psi I mu Si squared. Here you can disentangle the square by a Gaussian transform. So you introduce auxiliary variable lambda mu, and you have the Gaussian variable lambda mu, and then you have the coupling between lambda mu, psi I mu, Si. Simple computation. So this tells you that you have this exact form of the partition function. It involves two types of variables. There are spin variables, and there are these variables that I call pattern variables. The interpretation is, lambda mu is large when the system is very strongly polarized towards pattern mu. And so the S are binary. The lambda mu, they have a natural Gaussian measure. They are real variable with Gaussian measure. And the lambda mu and the S interact through this psi I mu, which are the patterns you want to memorize. So in terms of my beloved diagrams of interaction, I have now the green variables are the spin, the blue variables are the pattern variables, and I have an interaction between each spin and each pattern. And the strength of the interaction between I and mu, here, this strength is psi I mu. Now with this, I can use all my tools because I have gone back, thanks to that, I have gone back to a case in which I have IID disorder. On all edges, I mu, I have a new random variable, psi I mu. They are IID. So I can write BP, exercise, use the BP equations of yesterday, you use them here. And I can write the corresponding tap equations. The tap, Xi is the original pattern. The original, oh, sorry, yeah, maybe I forgot to mention this very crucial point. In Hopfield Model, you decide to study an ensemble in which the psi I mu are IID. It's not, you could decide to do something much more structured. You should. I will come back to it later on. But in the standard Hopfield model, psi I mu are IID. So if psi I mu are IID, and actually we will, so thanks a lot for the if psi I mu are IID, then you can write everything. And you write basically, these are the tap equations. Okay, I will not elaborate on that. They have been written many times. For some reason, there was some dispute, a little bit of dispute around these equations, but the first version written in 1987 was right, and it is still right. It does not, there is no problem with these equations. So this tells us something. It tells us that if I look at this problem of interacting spins, then depending on the choice of the ensemble, I get different results. I get a different phase diagram, I get different mean field equations, and so on. So the ensemble matters. It matters a lot. We have seen SK model, we have seen Hopfield model. Another ensemble that has been studied a lot are ensembles, and this slide is precisely for Gérard, because he was going to ask a question. There is the ensemble in which the J is generated as follows. You take a diagonal matrix, and you assume that you have an asymptotic density of the eigenvalues of the values of this diagonal matrix, let's say, but it can be anything, provided it has a limit. And you multiply it by a random orthogonal matrix. So you have a circular ensemble. You have an ensemble with rotational invariance. And the ensemble is that. D is fixed, but the ensemble is done by choosing the O, the rotation matrix. And it has a long history, and I quoted only Parisi Potters probably were the first to do it, and Marinari, Parisi, Retort, and there were many pieces of work, very nice works by Yoshiyuki Kabashima and so on. So perfect, these are already 3 ensembles that have been studied. Is that okay, and can we live with that? And I should say this ensemble here has also been studied recently in compressed sensing, for instance, or generalized linear regression, and that leads to the VAMP algorithm. When you do BP for this ensemble, or the equivalent of that, sorry, you get the VAMP algorithm. Is it enough? I think it is not. I have an obsession with the type of disorder that one should study, and I think that we are still very far, and that it is one of the main missing ingredients in the theoretical approach that we have had so far about machine learning, for instance. The missing ingredient is the structure of the disorder. So I insist a lot that basically I believe that if you think in terms of the success of deep networks, for instance, I think that this is strongly related to the task that they have to do. And the task is not an absurd task or whatever. It is a very structured task, and it is reflected in the fact that the data that you present is very structured. This is true for images. And the kind of structure that is present is, I call it combinatorial. Some people call it compositional. If you take an image, I take an image of this room. Immediately, I will say this room is composed of tables and people. And then I zoom a little bit and I say people, they are composed of the body and the head. And then the head is composed of eyes and glasses and the nose and so on. Everything is compositional, and it has an item is done from feature, which is built from sub-features and so on and so forth. Another success of deep networks has been on language. Language is very much compositional. It is structured. It is based on the smaller structures with grammar rules. And I wanted to illustrate that for the Indian colleagues here, because I came in my trip. I got to know François Grimal, who is one of the experts of Sanskrit grammar, and he has written 10,000 pages of analysis of the Panini grammar. Panini grammar is a grammar from 500 before Christ about Sanskrit, and it tells you how you can combine the words in Sanskrit. It's based on 10,000 rules of combination. So it's a purely combinatorial construction, and this just explains, for instance, how the word cross, with the meaning of intensely or repeatedly, is this word here, and it tells you how you combine several, here maybe 20 of the rules of Panini and so on, in order to get to the right presentation of the word cross. So it's a beautiful construction, but it is here in all languages. This one is probably in my mind, I know very little about it, but I'm fascinated by that. But it's one of the most purely abstract construction. So back to science, I am not able to study the Panini library. It would need a bit more work. I go back to the Hopfield model, and I ask the question that Sri was asking: why do you study Xi mu, which are IID? You should do something better. So I started to work on Xi mu, which are combined, and they are combinations. So the pattern Xi mu is a combination of features. The feature are UR, and I select the feature yes or no with a vector v mu r. I say v mu r will be +1 or -1, depending if I take the feature or not in my pattern. So I build the pattern from elementary feature. Sorry, I build the pattern from elementary features by superposition. And because I am not enough, because it's just the first step, I do just a linear superposition. It should not be linear, it should be more complicated than that. But let's see what happens if you do linear superposition. So I do exactly the Hopfield model, but with what I call a model of the world, which is a combinatorial composition of elementary features. And of course, I could go beyond. I could say that the feature is built of sub-features, etc. Let's look at the first step, and keeping to the linear manifold. So I look at the partition function. This is just algebra. And I disentangle all the terms by Hubbard-Stratanovich. Okay, I will not do the algebra for you, but it is written here. The result is very simple, very elementary. I find that I have three types of variables. I have the variables which are associated with the spins. I have the variables which are associated with the patterns. And in the middle, I have the variables which are associated with the features. They are coupled. And the coupling, they depend on the decomposition of the features, of the patterns on the features, and what feature has been taken is coupled to each spin. So you get this graph. Now you have IID variables on all the edges, and you can turn the crank, and you write the tap equations, for instance. The tap equations are BP equations, are messages sent here and there over the graph. So the resulting tap equation, they don't matter. I will not tell them to you. They just differ from everything because it's a new ensemble. New ensemble means new phase diagram, new tap equation, and so on. The thing that I like in this simple exercise is the fact that naturally, if you want to address this system of the Hopfield model with structured patterns, naturally you see appearing a 3-layer network in some sense. It's not feed-forward, but it has 3 layers. It has a layer of inputs, the spins, one which looks at the patterns, and in between the features. So this is very reminiscent of what happens when you have feed-forward network, in the sense that you have in some sense you have the input, and before you go to the final result that interests you, is it the pattern mu or another pattern? You have to look at an intermediate layer which tries to see what are the features which are present. And if you have sub-features, then you will have an extra layer of sub-features. So it has a nice structure that is reminiscent of what the feed-forward layers are doing. So this is just, I mean, it's just an evocation. I have not done anything about feed-forward layer yet on this.
So you had a particular structure to the pattern considered here.
Yes.
So if I were to sort of decorate that further, that would... Is that what you're saying? That would correspond to the emergence of additional layers in some...
Yes. If I iterate my construction, you see I had this.
This one, yeah.
I had this construction here.
Right.
I generate a pattern by superposition of features.
Right.
If the features are themselves superposition of sub-features, I will have another intermediate layer. And the thing which is nice is that spontaneously what happens is that you start with the spins, then you have the smallest features, and then the feature of larger scale, etc., until you get to the pattern. Okay. So now the question is to go beyond that, let's say. This was a very simple exercise in some sense, looking at the Hopfield model and trying to understand what happens when you have linear superposition of features. And so here I want to go to the last chapter of today's lecture, which is this hidden manifold model. So I go back to the heart of the activity of these days, which is feed-forward neural networks. I will look at a 3-layer neural network, one input, one hidden layer, and one output. And I will study that with, I will study how such a network can learn when it has structured patterns. So before doing that, one has to understand what is the type of structure of the pattern that one would like to look at. And so we did with Sebastian Gold, Florent Sakala, and Lenkas Deborova. We started with a number of numerical analysis of data, and basically we were using this kind of network. So this is the input, this is a hidden layer, and this is the output. We want to study it mostly in the case where n is large, but I will start with experiments, so n will be maybe 1,000 or something like that. And k is the number of hidden units, and we will vary it. So this is a network that implements the following function. The output is a superposition with weights vk of a nonlinear function g applied to wk times x. X is the input. Here, on unit k, I compute wk times x. I implement a nonlinear function g, and then I do the superposition. Is it clear? And the g could be whatever you like, a sine function, a ReLU, the one that you prefer. So I will use this as my tool, and we will use this network. We will first do some experiment, and we use 2 tasks in the experiment. First of all is a kind of typical task that you would like to do, and we decided that we would like to want to distinguish odd from even numbers in MNIST. Okay. Standard binary task that you could get from an experimental database. And the task 2 would be to use an output, a target output, that is defined by a teacher network. And my teacher will be a sine of some weight nu m G of omega m x over square root of n. So the teacher has more or less the same structure. It might have a different number of hidden neurons. It has m hidden neurons. This one had k. But apart from that, sorry, there is a sign missing there. I should put the sign when I look at the binary task. So this one is the teacher-student. The task 2 is a standard teacher-student, a generalization of the teacher-student of the perceptron that I was showing you before. It is a task that has been studied quite a lot in the 90s. And the task 1 is an experimental task with a database. We will monitor the training error, which is a difference of what is found in the teacher and the student, and the generalization error, that you compute the same thing on new patterns. We will also monitor something which is interesting, which is if you train 2 independent networks, either on task 1 or task 2, you start from a different initial condition and so on, and you train them, and you look at what is the difference of the function that they are implementing. Okay. So all that is done by standard things, stochastic gradient descent, etc., etc. You run the thing and you look at the experiment. So this is the result. So this is on NIST. You train on NIST and you look at the generalization on 10,000 patterns of NIST. This is a generalization error as a function of the number of hidden neurons, number of neurons in the hidden layer. And you see that this generalization error, it decreases slowly. Okay, nothing much to be said. Now, if you look at if you look at 2 different runs, 2 different experiments, starting with different initial conditions, etc., different random numbers, you run twice the gradient descent, and you look at the difference between the tasks that are performed by the 2 realizations of your network, and this is the orange. This is the orange task here, and the orange task tells you that you perform more or less with the same general. Basically, the 2 students, the two trials, they are the same distance from each other as they are far from the ideal target of the MNIST, which makes sense. Okay. Let's just forget about the green. Now I do the same thing with a task which is very different, which is a task defined by a teacher. And again, I look at the blue points, which are the generalization error, and generalization error, it decreases as when k increases, and in this case m was equal to 4, and so you see that when k becomes equal to 4, there is a transition to perfect generalization. The task that has to be done was defined by a network with m units. This one has k units. As soon as k is larger than m, there is a way to implement perfectly the result. And there is this transition to perfect generalization. It is the same as we had in the perceptron, basically. So this is what you get. But so they learn exactly the same function. Now, if you see, if you see what happens on what is the difference of 2 students in some sense. In one case, you had the green point that say, do they implement the same function or not? And on NIST, they do not implement at all the same function. They agree on the NIST, on the test set, but they are very different functions. On this one, they implement exactly the same function, which is a teacher. So this is the first difference. If I look at the learning dynamics, what I find is the following. This is epsilon g as a function of the number of steps in the learning dynamics. And you find that if I look at it on NIST, the 2 curves depend if you learn the two weights or if you just learn the weights in the first layer. They are more or less the same. You find a standard decrease of the generalization error rather smooth. Instead, if you have a teacher-student, what you find is that there is this plateau that develops, and after a long time, the neuron starts to specialize and you go to 0 generalization error. This had been noted in the middle of the 90s, and there has been a lot of work on that. So this is very different. Basically, all these experiments were to tell you, if you look at here, I was having IID data, and I was having in my teacher student, I had IID data and a task that is defined by a teacher. In NIST, I had NIST. And the phenomenology is very different. So there is something that is missing in the teacher-student approach. So what is the data structure that we want to put? So if you look a little bit more in detail at NIST, you find that, okay, as we know, an image in NIST is a point in 784 dimensional space. This is the input space. Now, of course, the image, they are very special configuration in this space. And you can start to understand, you may want to understand what is the manifold of the handwritten digits. It's not a very well-defined statement, but let us look at the manifold of NIST digits. And you want to, maybe you would like to understand the geometry of that. And so one way, the first thing that you would like to do is to understand, are they concentrated on a subspace, or are they filling the space? One way to do that is to look at the intrinsic dimensionality of this manifold. And this can be done by the following trick. It was invented, to my knowledge, in a different context by Grasberger and Procaccia, who wanted to understand, to measure the dimension of strange attractors in dynamics, in nonlinear dynamics. And the trick is the following. You have the points of the manifold. If you have p points and they live in a space of dimension d, then in a sphere of radius r, the number of points will grow like r to the d. Now, if you look at the nearest neighbor between 2 points, the nearest neighbor will be at a distance which goes like p, the number of points, to the -1/d. So there is a scaling law. And so the idea is to do a log-log plot of the nearest neighbor distance with respect to the p, to the number of points. And if they align and there is a slope, it gives you an idea of the dimension. This has been done. It has been done by several people starting around 2005 from NIST. And from NIST, you find relatively good straight lines. And basically, you find the effective dimension of the manifold of handwritten digits is 15. Maybe 16. Okay, I will not argue whether it is 15 or 16, but it's like that. Okay, but so it means that all these guys here, for instance, they are valid images of 700 points, but they are not handwritten digits. They are outside of this manifold. It also means, and this is something that I find is not enough done, not enough frequently done. It means that when you train a network to recognize handwritten digits, for instance, it should have an answer. It should be trained to be able to give an answer to say, this image that you present me, it is not in the manifold of the images that I have been trained on. So I don't want to answer. Just, okay, present me that. No, I have been trained on NIST. I have been trained on handwritten digits. I don't recognize that. I don't want to tell you if it is a 0 or 8 or whatever. So you can do a bit more detailed analysis. It was done here, for instance, and in other papers as well. You find that if you look at the manifold of the 5 has the dimension which is around 12. Manifold of the 1, it's more around 7. These are three different ways of measuring this intrinsic dimension of the manifold. They vary a little bit, but you see it's some smaller variations. So basically, you will find that the problem of NIST, it is very simple. You are in a 784 dimensional space. In this space, there is a 15-dimensional manifold of handwritten digits. In this manifold, there are 10 sub-manifolds of dimensions between 7 and 13. Each of them represents a digit. And you want to identify these sub-manifolds. So that's nice. you see the data. I mean, it's not that precise. You see, this is the data. So, I mean, yes, they have the best fit is 14.43. I mean, you will not rely on that. I mean, it's empirical work on handwritten digits. So there is not a sharp statement on that. But it's certain that it is not 35. Now, you asked me, is there a reason to believe that there is a manifold? I think yes, in some sense, because local deformation of a digit is still a digit. And so the question is, some local deformation of are still a digit. The smooth deformation, local compression, local dilations, and so. So we wanted to build an ensemble that captures some of these ideas, the ideas of a manifold, sub-manifold, and so on. So the idea is the following. We will generate patterns like by a superposition of features. So basically, this is the data. This is how we generate the data in our model. So we have input patterns, X. They are built from R features. So we have feature vectors, FR. And basically, what we will do is to take a superposition for each, to generate a pattern mu, we take a certain superposition of the vectors. We take the sum of CR, FR, and apply a nonlinear function f component-wise. So why do we apply a nonlinear function f component-wise? Just because of the following. If you just decide that the pattern is a superposition of features, linear one, then basically the whole activity in some sense, my space will be, there will be a subspace which is a linear manifold generated by the FR. And all the data will lie in this manifold. And the rest will not be explored. So if you look at the learning dynamics, there will be the standard dynamics inside the manifold. And outside the manifold, nothing happens because you don't have data. So this is trivial. But as soon as so the idea of the F is to fold this manifold. So you have, I never told you that, and it is not true, I never told you that the MNIST digits were a linear subspace. They are not at all. It's a heavily folded thing. So here, this is the folding function F. It is nonlinear. I don't have to say much more about it than the fact that it is nonlinear. So I have some patterns. They are built from superposition of the vectors, and then I fold all that. And that gives my input points. So the nice thing is that I can monitor the intrinsic dimension of the manifold, R, the equivalent of the 15 that I had for the thing. Now I have to define a, yes, please, Sri.
Say something about how useful it is to think in terms of these sub-manifolds?
How useful it is? What do you mean? What is?
I mean, have a large dimensional space, a low-dimensional subspace that can be constructed as something. That's useful.
Yes, it is useful.
Sorry?
Yes, it is useful. It's useful to know that.
No, but if it's not, it's a non-linear manifold. In terms of the practical utility, it's on the sphere, it's useful. That's the case, close enough. Yeah, no, I understand. But, it's something I don't have a good appreciation of. So at what point is it still a simplification?
I'm not sure. I'm not trying to find a simplification. I'm trying to find a way to generate data points which has a geometric structure, which has some of these properties that one finds in experimental database, like MNIST, for instance. So it does not need. Of course, I want it to be simple enough that I will be able to analyze. I will come to it later on. So that's why it's still, but I think that we really wanted to keep this idea that the data is on a manifold.
Is it clear that the folding function is the same for each one of the submanifolds?
Here I have not yet described the submanifolds. I have just described the manifold of data points. I will come to the thing now. But yeah, it's a good question. The answer is that we have not implemented that yet. So here is the task, actually. Here is where we have to decide what is the task. So basically, this is one of the possible points. It is described by what I call the latent representation. That is, its decomposition in terms of the basis vectors inside the manifold. But on top of that, there is the folding. The desired output, we will look at tasks where the desired output are function of the latent representation itself. They are not functions of the position of the point in the space. They are function of the position of the point inside the manifold, in the latent representation. Okay? So this means that basically the position of the point of the latent representation is a set of coefficients CR. It tells you what is the projection inside the manifold, what is the projection on the feature vectors. And so we will have a task which is just, let's say, like a simple perceptron applied to that. That is, it would be, I take the linear superposition with weight W tilde, that is the task. W tilde defines my task, and I apply a nonlinear function to that. This is the task. It could also be a task which is more complicated, like this one here. It would be the equivalent of the two-layer teacher perceptron, except it has something which is extremely different, that it does not apply to the X, it does not apply to the real pattern. It applies to something that I don't know, which is its decomposition on the generating vectors of the hidden manifolds. So now all the problem is defined by this equation. I have my data, I have a way to generate data points. I have a way for each data point to give you what is its desired task, and I can feed that into my experiment. Here, okay, it's a bit complicated. Maybe I will leave it aside, but it explains you that we have perceptual submanifold, that we have, with this construction, there is a set of directions in which the task is invariant. So the equivalent of the submanifold associated with each digit is present here. So here is, again, what we get for the generalization error, the blue points as a function of k. It's more or less stable, rather increases a little bit with k. And the thing that is very different from what we had in the original teacher-student scenario is the difference between two students. If I take two runs and I run my experiment twice, and I look at what are the tasks that they are doing, are they different or not? They are extremely different. And this is the same as what we got in NIST. So we have this phenomenology which is better. Now there was the dynamics of learning. So if I look only at the orange curve, which is a latent task, the latent task, it is given by like that. It is a latent task means that the target is defined by the internal representation within the manifold. And the plateaus, these famous plateaus that were not present in NIST, they have disappeared. So at least from the phenomenological point of view, from these two aspects, let's say, we started with this phenomenological difference between NIST on the one hand and the old teacher-student scenario on the other hand, and I was showing you two basic differences. Now, if I run, instead of the teacher-student, I run something with the hidden manifold model. I mean, I have data in a manifold, and the task is defined with respect to the manifold itself. Then I get a phenomenology that is much closer to what is seen in NIST. Now, the point which is important is that in some limit, this model can be studied analytically. And that is what I will show rapidly to you now. It is not easy, it's not obvious, because here you see that I am studying the dynamics of learning with such a network, and this network is presented some input, some database, and the database xi here, they are correlated. I will take as an ensemble some points in which the latent representation is built from IID composition. So basically I generate IID coefficient CR, and these coefficients tell me the decomposition inside the manifold, the decomposition in terms of the natural features. Then I have the nonlinear component, so the X are strongly correlated. And the fact that the X are strongly correlated makes life a bit complicated to analyze this thing. There is a solvable limit. It is a thermodynamic limit in which we will look at the case in which n here goes to infinity. The number of, the dimension of the manifold itself goes to infinity. And the number of patterns, the size of the database goes to infinity. And I fix the ratio, R over n is equal to gamma. So R over n is the dimension of the manifold divided by the dimension of space. And P over n is equal to alpha. And I fix K as a finite number. I take the case in which a machine has a finite number of hidden units. The function f? No, well, very weakly, I will show you. That is a surprise. First of all, the analysis can be done for any f. And actually, the result depends on only 3 moments of 3 specific moments of f. That came as a surprise. And now, so the ensemble is only these coefficients. The FR, which are the feature vectors themselves, I don't need to generate it from an ensemble. I can take a fixed set of vectors. I just need that they have some kind of balance properties. It's a bit like the RAP properties that were there for compressed sensing. I need that the coefficients are over the 1. I need that the scalar product of 2 vectors FR and FS, they are nearly more or less orthogonal. That is, the scalar product divided by n is order 1 over square root of n. And I can take a normalization condition. Now, the idea of the analysis is the following. Each component xi is a function of a certain quantity which I call ui. Ui is a superposition of the features. And basically, when you look at that, you can find that the second moment f of ui, f of uj, it is given by this expression here. It is directly related to the second moment of ui and uj, which I can compute. Now, the whole analysis relies on something that we call Gaussian equivalence theorem. It tells us that basically the very important variables are the pre-activation here. What is the field that arrives on the hidden neuron number k? This field, it is the sum of wik times an input which was f of ui. And it turns out that these various pre-activation fields, so they are a bit complicated because this is a nonlinear function, and the IID variable are at the level of each of the ui. Still, because of this structure, one can show that in the thermodynamic limit, these variable lambda k, they are joint Gaussian, and one can compute their covariance matrix. And their covariance matrix is related to the overlap between the weight vectors, and okay, I will not go into the detail. So using this Gaussian equivalence theorem, then it is possible to monitor the whole dynamics of learning in this system, and the model becomes solvable. Basically, and the thing which is very important that I have mentioned here, if you look at the moment at the covariance matrix of this pre-activation field, they depend on the function f. This is to answer the question of Gérard, only by 3 moments of f. They depend on f of u square average. The average means with respect to a u, which is a normal Gaussian variable. They depend on the average of f of u, and they depend on the average of u times f of u. So it means that the nonlinearity, and this came as a surprise to me. I would have thought that all our results would depend a lot of the function f that we take. We take strongly nonlinear, strongly, etc. Not at all. It depends on these three things. It means that for every function f you give me, there is an equivalent quadratic function f of u equal alpha plus beta u plus gamma u squared, which has the same result. This is, of course, it is applied point-wise. It is applied component-wise. This is something that has. So using this Gaussian equivalence theorem, one can compute the learning, and basically the thing that we did most extensively is the analysis of online learning. So online learning is a process in which you do SGD, but at each time you present one new pattern, and you never feedback on the database. You have just one run through the database. This is simplest to analyze, and that is why we started with that. So basically, it is described by the dynamics of weight, which is the usual gradient descent dynamics. And because you have a new pattern at each time, you can analyze it much more in detail. And basically, it was done by David, who is here, so David, Saad, and Sarasola in '95, and there were many other papers doing that. There was a whole activity on analyzing online learning. Basically, the thing which is interesting is that you can follow it by writing ordinary coupled differential equations for order parameters like this WKL. WKL is the overlap between the weights on hidden unit K and the weight on hidden unit L. And you can write coupled equation for that. It's much more complicated here. I will not write to you the equations. I will just give you the results. This is the theory. The theory is just solving the ordinary differential equation for the order parameters, which is very simple to do. And the points are the simulations. So this is a generalization error. And this is following some of the order parameters. This order parameter W is just the overlap between between the weight vectors of two hidden units, and sigma is some other generalization. Again, you have the points, and you have the theory. So it shows you that the ordinary differential equation is perfectly able, is right. It gives you the exact description of the system. Actually, it also gives us an idea of what is taking place. For instance, we have this order parameter, which I call RKM. RKM is a bit complicated. W tilde is the vector of weights that defines a task. So it was a vector of weights that you were applying to the latent representation in order to define the task. And then for the actual network that we are studying, we can look at its weights on the hidden unit K, but projected on FIR, projected on the feature vector. And this I call SKR, projection of the weight on the feature vector R. And so what I find is that there is an order parameter which tells me this SKR, how far is it from the hidden vector of the task. And you find that basically if you follow these various order parameters, they all follow more or less the same trajectory, and at some point they specialize. That is, there will be one which is R21 which goes up, and R12 which goes up. So it means that some of the hidden units of the students, they pick up some direction, hidden direction of the task in the manifold, which is not at all trivial a priori. And that is where the generalization really drops completely. No, because, okay, sorry, I should say this is 1, 2, and 2, 1. It would have been, the colors are not well chosen. The indices are not well chosen. If you change of course, there is a degeneracy of the indices. If you decide that the k equal 1, you call it k equal 2, then you will find that you have a perfect overlap between, you have overlap which is large between hidden unit 1 in the student and hidden and parameter 1, and the other one, they are decorrelated, of course. This is to show that, I told you that the Gaussian equivalence theorem, it did not rely on a random matrix. The matrix F could be anything, provided it is well balanced, let's say. And this is to show that it is correct experimentally also. So in order to check that, we applied it to a Hadamard matrix. So this is not taken from it's a case where F is Hadamard. It's not taken from an ensemble. And again, you see that the prediction and the experiment work very well. This is to tell you that, yes, but I will not be able, I'm not sure I will want to do that. This is just to tell you that one can also address with this method, one can address the full, not only the online learning that I was saying, but what happens when you do the optimal learning. And when you do the optimal learning, basically you want to understand, you imagine that you have the database, you know the database, you can cycle through the database as many times as you want. You want to find the best result for the learning with that database. How does it differ from the task that you had to do? This, in statistical physics, is called Gardner's computation. It is a probability or the volume of the space of weights that is compatible with the data. You compute it. This is a partition function. And it turns out that you can compute the log of this partition function using replicas. And the thing which is not, and I mean, certainly not enter into the replica computation here at that time, but it exists. And the thing which is interesting is that one can compute it in this case using, again, the Gaussian equivalence theorem, because basically the intrinsic variables that come in, they have an equivalent Gaussian distribution with known covariance. So it can be done using the same method. Some people believe that it cannot, but I say that it can. Just to say that there is a little bit of controversy on that. Yes. There is one last point that I want to address, that this model that I have shown, it is connected to some other branch of work on neural networks, on feed-forward neural networks, which is some work on random features. So this is, again, my network. It is a network in which I have an input layer, a hidden layer, an output, and the patterns that I present, they are correlated, and they are correlated because they belong to the manifold. Now, there is an alternative way of describing it, which is to say, oh, imagine that I put here an extra layer, and this would be the layer in which I have the values of the coefficient CR, the projections on the features. These ones, they are IID. So now, from this, I can feed into that, and I generate the value of Xi. I have quenched variables, FRI. They are fixed. These are called, and so this network here, it has been studied also in the literature. It is called a feature network. Basically, you have a certain layer of input, you generate from this input, and they may be IID, you generate from it, through a matrix F, you generate some features. And then you try to decode these features, you try to learn your network. This is fixed, you cannot learn that, but you learn all the rest. So, in particular, I want to point to the recent work by Montanari and May, and another extension recently by Montanari and other collaborators, in which they have studied this feature model in a simpler case, in a case where it is the output, the network that you study is a simple linear regression. It's not even a perceptron, there is no nonlinearity, it's just linear regression. And so this is a kind of a simpler version of what we have been doing. And Montanari and May were using that in the case in which F is generated by as a random matrix. And using, using results from random matrix theory, they could show that this is statistically equivalent to a case in which the X mu would be generated as just the linear superposition without the nonlinearity plus noise and plus a constant. And you see that here you have 3 parameters, and the 3 parameters are the ones that you have to fit in order to get the correct value of f of u squared average, f of u average, and uf of u average. So all these are equivalent. So there is an equivalence between the feature model, a linear feature model with noise, and our hidden manifold model. In their case, it was proven with random matrix tool. In our case, we don't need the random matrix tool because we just can work with a fixed F. I showed you the result for Adama F, provided the F is balanced. So just to summarize, we have a generative model for data and for task. The data lives in a hidden manifold. It has a latent representation. The desired task is defined in terms of this latent representation. This hidden manifold does not have the pathologies of teacher-student setup. It has a good phenomenology of learning, more or less similar to what we observe in NIST. And it can be studied analytically in one regime, which is a regime in which the dimension of the hidden manifold scales, it diverges in the thermodynamic limit, it scales linearly with the dimension of the space. I am not able to study the case in which it remains finite, let's say. That is another, it requires other technique. Okay, that is what I have at the moment for correlated data, but I think it is an important field which one should study in the next decades. Thank you.
Yeah, questions?
Well, I think it's an interesting question you raise. I have not seen, personally, I like this idea of describing the MNIST problem as finding 10 sub-manifolds inside a 15-dimensional manifold inside a 784-dimensional space. We have these scaling properties for the nearest neighbor distance, which point towards the existence of these manifolds and the value, but we know very little. At least I have not seen, maybe there are some studies that I have not seen, it's quite possible, but I have not seen more detailed study of the geometry. But as you mentioned, the very fact that it can be learned and it can be learned easily means that the geometry should not be that complicated in some sense.
So the results that you showed us were for k equals 2, m equals 2.
Yes.
Same number of m and k. Is there a risk when k is greater than m that you will actually represent a combination of features that the student nodes will
we have not seen that. We see a specialization with some of the hidden units we specialize towards one of the direction inside the. We have not seen a superposition, but we have not yet done the extensive study. I mean, I must say. I mean, we have basically found out how to write this ordinary differential equation and check that they are correct, which is what I have shown you. But we have not yet done, and we are starting to do now, a much more systematic study using this ODE, because having the ODE, it makes life very simple, much faster. You don't have to do all these heavy simulations. And using the ODE, we can explore a lot of these questions about what is the role of Km, the intrinsic dimension of the manifold and things like that.
And the other comment I have is about the pathology of these plateaus in online learning. My understanding is that they result from the symmetries that you, so for instance, each one of the hidden nodes doesn't actually know which teacher node to follow. And I think that this does not exist in real data, or hardly exist in real data.
Yes, that is true, but I think there is another interpretation to that. It is the fact that during the learning phase, the neurons in the intermediate layer, more or less, they are on the equal basis, and you see it on the curve that I was mentioning. They start doing all the same thing, the same learning, and it takes time until they realize whatever it means that they have to separate, that they have to take different directions so that they collaborate to give the right output. So I think it's not only, I'm not sure it is related to symmetry, but to the fact that there is this.
The reason for this, why I'm saying symmetry, because the level of fluctuations that you have has an impact on the plateau, the length of the plateau. So they are all looking for, I mean, if you choose them completely randomly, they're sitting in the middle between.
Yes, 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 yes.
But it takes time for them to break away.
Yes, that is true. The thing which we have not yet understood completely from this point of view is this one here. You see, this is the dynamics in this representation, in which basically you look at the direction of the weights for each of the two hidden units, and you have a way to project it towards the underlying task. And you find that they specialize after 100 time steps. That is also taking place in the usual teacher-student thing. But in the usual teacher-student, it results in a big jump in the generalization energy. And here, if you look carefully, there is a very small jump, but it is very, very tiny. So it has been completely. And it would be interesting to see if in real experiments with NIST and so on, there is at some point a small jump also or not. Hard to say.
To come back to it seemed that your Gaussian GET, whatever it was, Gaussian equivalence theorem, is the engine for the proof of these things. What is it? Is it a new central limit theorem?
It is, yeah, it is a kind of central limit theorem. It's a bit specific. Oh, yes, sorry. I don't know which slide is best. So you have these inputs here, and the input xi, they are nonlinear function of these guys. So these guys, a priori, they are just joint Gaussian, because the C are IID Gaussian. So they are just joint Gaussian. Then you take a nonlinear function applied to it. And then from that, you take a linear superposition with many of them. Okay? So the W, they are whatever, provided they are well balanced. So there is a condition, and actually this is a condition that is tricky, and if you want to get out of what we have done, if you want to convert it into a mathematical proof, at some point there will be some difficulty, which is to be sure that you control these quantities here. They have to remain all over the one. So it means that basically you are not polarizing the W. They are not going in the same direction, each of them. They are not polarizing too much to the other vectors. And so there is a kind of balance condition. Apart from that, they are anything. And so the only randomness is inside the U, which is this guy here. So it is a bit of a sophisticated central limit theorem in some sense. And it is not I'm not sure if it is a trivial one or if it is known in some other context. It might well be. We derived it by it relies a lot on the scalings which are there. I mean, the fact that we have the correct 1 over square root of n, the fact that the W are balanced and the F are balanced, they are very important.
microphone there.
But then because you have a thermodynamic limit, your local fields become independent of the input. Your local fields have become independent of the input u. Lambda tilde.
No, they are correlated with the u.
So I don't see it here in the expression for the correlation between lambda k and lambda L.
No, here I just look at the covariance between lambda k and lambda L, but I could also write a more generalized, I can look at the correlation between lambda k and u. It also exists.
Okay. And a second question about the labeling function. So you have a data generating model, which is, let's say, features that come together linearly with some nonlinearity. And how do you think about the teacher that labels the data?
How do I think about
how do you label the data? The second model where you have a summation of over W tilde times CR.
Yes.
How do these results depend on that model?
Oh,
Should it be
very little, very little. I mean, you could look at basically look at this one, which would be a kind of perceptron in the latent manifold, or this one, which would be a two-layer network applied to the manifold. We don't see much difference in the results.
Because if I follow your analogy with the random feature model, my data is being created by a random feature model. I'm labeling this data using a given perceptron. So conceptually, it is quite the same as the analysis that we do for the standard perceptron model, except that the data generating model is slightly different.
No, the thing that is the real crucial ingredient is the fact that the labels, they are not dictated by the positions of the points in the space, the x. They are dictated by the decomposition of these points on the features in the manifold.
Yes, yeah.
You have, I mean, if I would draw you have the points, they live in this manifold here, okay? And then inside this manifold, maybe I could have a simple separation rule related to a perceptron. So I would say these ones up to here, they have a certain value, and these ones, they have another value. That would be a kind of very simple perceptron rule inside the manifold. But because of the folding, it can make life quite complicated for the person. Because it is folded and you don't know the manifold. So in some sense, one of the things that we would like to do, but all this is very recent, as you see, so I don't have the answers to all these things, but we like to understand in the learning, what is a part of the learning that has to do with understanding the manifold, by the learning by the system, by the neural network. What is the part that has to do with understanding the manifold, and what is the part that has to do with understanding the rule? Because in our case, if you have understood what is a manifold, then it's easy in some sense, because you just have to project back onto the manifold, and you will find a simple rule. This is a big surprise. This is a big surprise. It is there. It is there. Then there is, I mean, I think that the ABC, they tell you, it's a statistical statement. They tell you that two manifolds that are completely different but have the same ABC, they will have the same performance and they have the same behavior. It doesn't tell you that the manifold itself is important.
Any other questions? Okay, so if not, let's thank Marc again for a great set of lectures.